Thank you for the introduction. I would also like to thank the organizers for inviting me here and allowing me this opportunity to present some of the current work I've been working on for the last few weeks or months, I guess. So, as the title says, it's Fourier-Wigner multipliers in quantum harmonic analysis. And I will start with some notation and background, mainly to set the stage and ensure we're all on the same page before we continue. I will also try to give some background and motivation of why I started looking into this. And then I will continue introducing quantum harmonic analysis. I'll try to be brief because we've already seen quite a lot of talks, at least yesterday, on quantum harmonic analysis. We'll then transfer to Fourier-Wigner multipliers, mention some of the results I found. I include some proofs which are quite short and easy to show, but there's also quite a lot of details I will be skipping. Towards the end, I also have some references. So even though it says Fourier-Wigner multipliers, I do not actually have the Wigner distribution in my talk. Just a small disclaimer. So let us just start by recalling that S denotes the Schwarz class of rapidly decaying smooth functions, and we denote by S prime its dual space of temper distribution. As is common in quantum harmonic analysis, we consider not the Fourier transform, but the symplectic Fourier transform, which plays a crucial role in what I'm going to talk about later. And we can extend the symplectic Fourier transform to the temper distribution using a dual pairing. And I will always consider Cesky linear dual pairing, as it goes well with the symplectic Fourier transform. And it also makes all of the formulas nicer, I think. So what are the classical Fourier multipliers? Well, we start with a bounded measurable function m. Then we consider the linear operator, where we first take the symplectic Fourier transform, we multiply it with our function m, and then want to take the inverse. But the inverse of the symplectic Fourier transform is, again, the symplectic Fourier transform. And so we end up with this operator here, which are a priori acting on Schwarz functions. And we denote by MPQ the set of all such functions, for which this operator Tm then extends to a bounded operator from LP to LQ. And we equip it with a norm, which is simply the operator norm from LP to LQ of this operator Tm. In the case when P is equal to Q, for simplicity, we simply just denote it by MP. And there are some known facts about these multipliers. All of this can be found in Graphaco's books, for instance, on classical Fourier analysis. So if P is greater than Q, then the multipliers consist of only the trivial multiplier, which is the zero function. The adjoint operator of the multiplier is you're taking a complex conjugate of it. And you can show that it's a multiplier from LP to LQ if and only is from LQ prime to LP prime, where the prime denotes the Helge conjugate. When we consider MP, this actually is a Banach algebra. And there's a classification of M2 and M1. So the M2 consists of all bounded measurable functions, while M1 is the Fourier transform of the complex Radon measures. They are also nested. So these were some of the properties I wanted to look into. And one of the reasons I started looking into this is there's a known multiplier, which is the Bochner-Riesz multiplier, where you integrate over the unit ball, then you consider 1 minus the absolute value squared, and this raised to some positive delta. There's a famous conjecture about this multiplier saying it's bounded on LP, if and only if you have this range here. And there are known examples if you go outside. So the main reason that motivated me to look into this is there's a famous paper by Terence Tao from 1999, which states that the Bochner-Riesz conjecture actually implies what's known as a spherical Fourier restriction conjecture. The restriction conjecture is something I've been interested in for a few years. So what does the restriction conjecture says? Well, in simplicity, you take the Fourier transform, you restrict it down to the unit sphere. Then you ask, when is this a bounded operator from LP into LQ on this unit sphere? Equivalently, we can look at the dual formulation, which is also the one which is most studied, which is equivalent, where you start with a function on your sphere, you multiply it by the surface measure of the sphere, and then you take the Fourier transform of this. This will then take a function on the sphere and then extend it to a function on all of RD or R2D for the case of the symplectic. There are two ranges for which are conjectured that it should be bounded for these, and there are known counterexample. The first one is actually quite easy to see. If we consider the constant function, since you have a finite measure on the sphere, this is always integrable on the sphere. But by the method of stationary phase, you can get decay estimates for the Fourier transform. In particular, you can write it in terms of Bessel functions, and then you know that it's in LQ prime if and only if you have this range. The other one comes from a homogeneity argument, where you consider spherical caps of different sizes, and you want it to be bounded uniformly on the sizes, which leads to this. And in a recent paper, together with Franz, we show that for compactly supported measures, the classical Fourier restriction is, in fact, equivalent to quantum Fourier restriction. And by quantum Fourier restriction, we mean we take a Schatten operator, we take its Fourier-Wigner transform, I'll get back into the Fourier-Wigner transform, and we restrict it to the unit sphere. And then we ask, when is this a bounded operator from Schatten P into LQ on the sphere? And so my thought then was, well, is there a quantum formulation of the Bochner-Riesz conjecture? And if so, does this imply the quantum Fourier restriction as we had in the classical case? And for this, we first need quantum harmonic analysis. Let's just recall that we have this symmetric time frequency shift. And with this, we can define the ambiguity function by taking the inner product of F and then let rho of Z act on G. And using this, we also have the Weil quantization, which we write as this weakly defined integral here. And this has to be understood in the following case, that we let the operator act on a Schwarz function, we take the dual pairing with another Schwarz function. This is the same as taking the dual pairing now in the double variables of the symplectic Fourier transform of the symbol, and then with the ambiguity function, where we then switch the order of psi and phi. This has to do with the Cesky linearity. And so we then can define this other space S, which is then the class of Schwarz operators. Namely, we're looking at the Weil quantization of all Schwarz functions. And again, we can consider its dual space of tempered operators. So quite quickly, the Schatten classes are then the compact operators on L2, for which the singular values lies in some small LP space. The singular values we get from the singular value decomposition. And then we equip it with a norm, which is the small LP norm of the singular values, which then turns it into a Banach space. And so we have these convolutions in quantum harmonic analysis, which were introduced by Werner in 1984, where we first had an operator convolution, where we replaced the integral by the trace, and we have this operator translation, which simply just translate the Weil symbol. Similarly, we have a function operator convolution, again, where we integrate F, and then we have this translation of the operator. This is, again, considered weakly. And so one of my main tools throughout most of what I've done is the Werner-Young's inequality, which gives us Schatten estimates with this convolution. And it's similar to the classical one, where we have 1 plus 1 over R is equal to 1 over P plus 1 over Q. And then so for function, say a function in LP and an operator in SQ, then the convolution is in LR. And it's using this operator is quite a cool way to go from operators to functions and back and forth. Of course, you have to pay a price, which comes with this convolution. And so we have this Fourier-Wigner transform as well, which were also introduced in the same paper. Where again, we replace the integral by a trace, and then we replace the complex exponential by the symmetric time frequency shift. And there is a version of Riemann-Lebesgue which then ensures that if we start with a trace class operator, this is continuous and vanishes at infinity. Similarly, extends to an isomorphism from the Hilbert-Smith to L2 on phase space. I mentioned this result here. So for Schwarz operators, they've been extensively studied. And we also have these properties of the classical Fourier transform that the convolution turns into products. And so what are then the Fourier-Wigner multipliers? Well, we consider the classical Fourier multipliers and then we simply define them in a similar manner. Namely, we take a bounded measurable function, then we take the Fourier-Wigner of a Schwarz operator. We multiply it with our function, and then we take the inverse Fourier-Wigner again, which then becomes this weakly defined integral here. And then we say that, well, if we consider all bounded measurable functions such that this Tm then extends to a bounded linear operator from the Schatten P class to the Schatten Q class, and then again, we simply write MP when P is equal to Q. And so one quick remark is that, is this a natural way of doing it? And I think so, yes. But we also have that it commutes with the wild quantization, which is that if you take a classical Fourier multiplier, apply it to a Schwarz function, and then take the wild quantization of this, this turns out to be the same as first doing the wild quantization of the same Schwarz function, and then doing the Fourier-Wigner multiplier applied to it. In particular, we can conclude, also using the isomorphism of the wild quantization, that the multipliers on the Hilbert-Smith operators are exactly the multipliers on L2, which we know are L infinity. But as was told in the first talk yesterday, is that quite often P is equal to 2 is not the most interesting case. So let me make another remark, is that we can write the Fourier-Wigner multipliers as convolution operators. So this is purely formal. You can do it more rigorously. But the idea is that the multiplier is the same as doing the convolution with the symplectic Fourier transform. So this is, then again, the distributional symplectic Fourier transform. And this is kind of interesting, because if we now consider a rank 1 operator, so we take two functions in L2, and we choose some multiplier in this MPQ class. We let it act. We know that it's a convolution operator, but the convolution with a rank 1 is the classical time frequency localization operator, which have been studied quite a lot. In particular, if we restrict instead of L2 to the fighting algebra, we get this norm bound in terms of the norm on the fighting algebra. And so we can then conclude that if we have a multiplier in MPQ, then the symplectic Fourier transform has to be in the modulation space MQ infinity, which I think is rather fascinating. So let's take a step back. We noted that for the case when P is equal to 2, there's an isometry. And because of this, the classical multipliers coincide with the Fourier-Wigners. So a natural question is, well, does it always do this? And the short answer is no. So we have a short lemma here, which says that if P is greater than Q, then in fact they do coincide because everything is a trivial multiplier. When Q is greater than P, we can actually find a Fourier-Wigner multiplier, which is not a classical Fourier multiplier. So I've sketched a short proof of this. So we first start when P is greater than Q. We consider this map. It looks quite bad, but the idea is that we take an LP function, we convolve it with a rank 1 operator, which is the L2 normalized Gaussian tensor with itself. And by Werner-Young's inequality, we know that, well, this is a Schatten P operator. We can then apply a multiplier to this, which again gives us a Schatten Q multiplier, and then we convolve it again with the same rank 1 operator. This will then give us an LQ function by Bochner-Riesz inequality. But if we then consider the symplectic Fourier transform of this, everything reduces down to simply the Gaussian times this multiplier times the symplectic Fourier multiplier, symplectic Fourier transform of the function. In particular, this has to be a classical symplectic or a classical Fourier multiplier from LP to LQ, and so it has to be identically equal to 0 because P is greater than Q. But the only way for this to be identically equal to 0 if the measurable function m was 0 to begin with. For the other case, you simply consider the constant function 1 again. You know that the Schatten classes are nested, and so this multiplier, which coincides with the identity operator, is a bounded operator from LP to LQ because of decreasing norms in the Schatten P. But there's no way of comparing LP function and LQ function for P not equal to Q. So this cannot be a classical Fourier multiplier. So then there's this result here, which I found is kind of interesting, because if we add an additional condition, namely that the multiplier has compact support, then they're all comparable again. In particular, some consequences of this is that if we consider the multiplier of the unit ball, and this is bounded on Schatten P if and only if it's P. This is a classical result by Pfefferman from the 70s. Moreover, if we go back to the Bochner-Riesz, we saw we were integrating over the unit ball. In particular, this has compact support as well. This is bounded from Schatten P to Schatten P if and only if the classical one is bounded from LP to LP. So we can then conclude that, well, quantum Bochner-Riesz then implies quantum spherical Fourier restriction. The argument is that, well, the quantum Bochner-Riesz is equivalent to the classical Bochner-Riesz, but the classical one implies the classical Fourier restriction. But by the previous result, together with Franz, we show that, well, they are equivalent again. So the classical spherical Fourier restriction implies the quantum spherical Fourier restriction. So the way we prove this theorem, we need an auxiliary result. So this was originally used to prove equivalence between classical and quantum decoupling. And the statement is, if you have a bounded set, then there exists L2 normalized Schwarz function G and H and a constant depending on the set. So the functions as well depend on the set. Such that if we have a temper distribution and its symplectic Fourier transform is supported on this set omega, then we can bound the LP norm in terms of this constant times a convolution with this rank 1 operator in the Schatten P norm. Similarly, if we have a tempered operator and its Fourier-Wigner transform is supported on omega, then we have a similar statement. Now we can bound the Schatten P by the LP. So the idea for the proof is then that, well, we start with a tempered operator and say a Schwarz operator. We can note that the Fourier-Wigner multipliers, they commute with the classical multipliers when we are looking at convolutions. And the easiest way of seeing this is simply you take the symplectic Fourier transform, they have the symplectic Fourier, same symplectic Fourier transform. Since the symplectic Fourier transform is an isomorphism on the tempered distribution, they have to be the same. In particular, if we take a classical Fourier multiplier, then we note that if this has compact support, then Tm of T has also compact support. In particular, we can bound the Schatten Q norm by a constant times the LQ norm of this convolution. Then we can rearrange it in terms of the classical Fourier multiplier. Then use that, well, this is a classical Fourier multiplier, so we can bound it by the multiplier norm times the LP norm of this convolution. And then we simply conclude by applying Bochner-Riesz inequality to this convolution. And note that since G and H are L2 normalized, then the Schatten 1 norm of this rank 1 operator is 1. And then we have shown that, well, we can bound this operator by some constant times the classical multiplier norm. So this has to be a Fourier-Wigner multiplier norm, Fourier-Wigner multiplier. So for the other direction, it's the exact same argument, but you use a different statement from the previous result, and then you reverse the order more or less. And so that's all I wanted to say. So these are the references that were included during the talk. And with that, I would like to thank you all for your attention.